Today we're talking about arithmetic sequences, and just as a reminder, the word sequence means a list of numbers that establishes some sort of pattern. Usually it has a pattern. So a sequence is when you have a list of numbers that just keeps going and going, and if you can find the pattern between them, then you can extend that sequence further and further, as long as you know what the pattern is. And our focus is going to be on arithmetic sequences today, which mean that the difference between each pair of consecutive terms is the same. So each number in the sequence is a term. So I would call this my first term, second term, third term, fourth term, and so forth. And when the difference between each of the terms is the same number every time, that's called an arithmetic sequence. And the difference between those two numbers is called the common difference. Okay, so the difference is called the common difference, and then you can always then find the next term in the sequence by simply adding that common difference. So in this particular example, you can see we started at 5, and if you subtract 10 minus 5, 15 minus 10, 20 minus 15, we end up always getting a difference of 5. So our common difference here is 5. If I wanted to extend this further, all I would have to do is add 5 to 20, and I would know the next term is 25, and so forth. So if this feels like it has some resemblance to a linear, you're absolutely right. An arithmetic sequence is essentially a sequence that represents a linear relationship. And all lines, usually we look at it as an equation or a table of values, but you can also express it as a sequence. So the arithmetic sequence has a formula that looks like this, and this is what we call the explicit formula. Write that down. And the explicit formula is a formula that gives you enough information. It tells you what number you're starting at. It tells you what the common difference is. And you can use it to then find any term further down in the sequence itself. So let's break this down. The notation here that you see for A represents the actual term in that sequence, and N represents the position. So if it's the 10th term, or the 3rd term, or the 54th term, that's what N represents. So this notation right here is the way that we write the nth term in the sequence. Right? Logically, then A sub 1, little tiny 1 here next to it, is the first term in the sequence, because that's what the n represents, is the term in the sequence. So when I see a 1, it's the first term. It's the number that the sequence began on. And then the D value here, it represents the common difference. Sorry about that. So, and as long as you have those ingredients, you should be able to find any term further down in this. So all you have to do is plug into this formula here, and then the big thing with the arithmetic explicit formula is that after you've entered everything, you want to make sure you simplify that formula afterwards. So we'll see what that looks like in our examples. All right, so first of all, let's talk about some of the more basics here of being able to identify if it's an arithmetic and or determine what that common difference is. So let's take a look at the first 6 here. We won't do all of these. We'll just do a couple of examples. It says write the next 3 terms in their arithmetic sequence. So if we can identify the common difference, then we can go ahead and extend the pattern after that. So let's try number 1. So on number 1, we have 1, 8, 15, 22, and they already told us it's an arithmetic. So actually one way we can definitely check or find the common difference is take the difference between the new and the previous. So if we do 8 minus 1 is 7, and you can test that a few more times. 15 minus 8 will also be 7. 22 minus 15 will also be 7. So the common difference is a positive 7. And once you know that, you can just extend the pattern by adding 7 to 22, and so on. So after 22 would come 29, and then 29 plus 7 would be 36. 36 plus 7 would be 43, and so on and so on and so on. And you just put your three little dots if you wanted to say, hey, the pattern is going to keep going. Okay. All right. Let's try number 2. So on number 2, we can see that this is decreasing. They've already told us it's arithmetic. It's a decreasing one, which means our common difference will be a negative number. And that is okay. We can still find it by subtracting the new minus the previous. So 14 minus 20, that's negative 6. 8 minus 14 is negative 6. 2 minus 8 is negative 6. So our common difference here is negative 6. And we can use that then to continue the pattern. If I am a 2 and then I add a negative 6, or in other words, subtract 6, we're going to be at negative 4 then. And then negative 4 plus a negative 6 is a negative 10. Then a negative 10 and a negative 6 will be a negative 16. Those are the next 3 terms in the sequence. Okay, so try number 3 and see how that goes. So if you got a common difference of 9 here, and then the next 3 terms were 48, 57, and 66, then you are right on track here. That's what an arithmetic sequence is. It's just a list of numbers that has that familiar linear pattern where they're adding or subtracting every time to get the next term. Okay, so let's practice a little bit of graphing. So on 7 through 12, we want to graph the arithmetic sequence. This is really not very different than the other graphing you have done this year, but you might be asking yourself, well, how am I going to graph on a XY coordinate grid if I only have one list, right? Good question. So the way that we graph our sequences is the independent variable, or the input, is actually the position of the term. So that means that before I go to graph this, to generate actual ordered pairs, I'm actually going to turn my sequence here into a little bit of a table compared to the position of that number. So up here, I would just say, okay, the first term is 1. The second term is 3. The third term is 5. The fourth term is 7, and so forth. That top row that I'm creating is just marking what term in the sequence it is, and then over here is that a sub n, which is the actual value of the term. So when I graph this, the x-axis is going to represent the position, and the y-axis is going to represent the actual value of the term itself. And let's see, so we're only going up to the fourth term, so we definitely can go here just by ones. So, and so on here. And then I think these will fit okay. So we're probably just going to go up by ones as well. 3, 4. Okay, so let's actually plot our points here. So we would say the first term in the sequence was 1. So that would be this ordered pair. So the first term in the sequence was 1. The second term in the sequence was 3. So the second term was 3. The third term was 5. So I go to the third term, go 1, 3, 4, 5. There it is. So the third term in the sequence was a 5. And then the fourth term in the sequence is a 7. So fourth term was a 7. Okay, and for those of you, again, I'm just going to reiterate this, that feel like this really feels like a lot like a linear, you're absolutely right. Check it out. So if I put a straight edge against this, these points are exactly on a linear or a straight line path. Excellent. Okay, so that's graphing. So now you know you can graph your sequences by basing them on the position versus the actual value. Let's go ahead and flip that over. Got a couple of more examples here, so let's try one more graphing example here. Let's try number 11. Number 11, try it on your notes first, and then you can check your graph. So check number 11, see how your graph compares on your notes to the one we have here. Again, you compare based on the position, so our ordered pairs would have been 1, 1, 2, 4, 3 comma 7, and 4 comma 10, which if you go by ones on your axes would look like this. Again, the x-axis represents the position of the value on the sequence, and then the actual value is your y-axis. All right, so let's talk about actually identifying whether something is arithmetic. So the ones they've given us, we already knew we were arithmetic, and we were just extending them, finding common differences, and graphing. But let's talk about how we would identify. So we talked a lot about how this really demonstrates a linear pattern. And so you have a couple of ways. If it's graphed for you, you actually could see if it's even close to a straight line, in which case you can still want to point, check your points, but you have a good idea that this one might be arithmetic. Versus here, if I connect any 2 points here, the rest of land on that, right? So I can see very quickly here that I cannot, these are not a straight line. If I connect these two, then the other two are not on there. And you can confirm this with that common difference. So if we do 1 minus 0, that's a difference of 1. 4 to 1, that's a difference of 3. 9 to 4, that's a difference of 5. So clearly not linear. And the graph, so this one's no. Since the graph itself is not linear, then that means that this is not arithmetic. And we confirm that with checking that common difference, or checking the difference and realizing it's not a common difference. Okay, but this guy here, I can put my straight edge up against any two of those, and then all the points are on there. And I can confirm that, just to be safe, with my common differences. So 30 minus 20 is 10, 40 minus 30 is 10, 50 minus 40 is 10. So the answer here is yes, this is arithmetic. That common difference is 10. I can tell that by the graph. The graph is linear. So yes, this is arithmetic. Okay. All right. Now, remember that equation we talked about on the front page? Here's the time we're going to use it. We're going to use it to, first of all, we're going to write it from a sequence, but then we're going to use it to find the 10th term. So it's nice when they tell us, oh, find the next 3 terms. We can just use that common difference to just extend the pattern a little bit, and it's pretty simple. However, if I wanted the 43rd term in this sequence, right? I think you'll agree that we don't really want to sit here and try to extend this to 43 values. That would be, imagine if I asked you for the 310th term, right? We want to have an alternative if we are, instead of just finding the very next few, if we need to find a term further down the line. That's where the equation comes into place. So to remind you, since we have it on the other side of here, this is what it looks like. You can find any term in the sequence by taking the first term plus, and then the book puts the d behind. I kind of like to put the d in front, but it doesn't matter, right? We know multiplication is commutative. So I like to, because I distribute this way more often, I like to put the d in front, but you can do it either way. So that is the explicit formula. We can, as long as we can identify from this sequence what is the first term and what is the common difference, those are the only ingredients I need to simplify this out and find out the explicit formula that will help me find any term. So let's start with number 16. So number 16, I want to identify 2 things every time. Okay, I want to identify what is the first term and what is the common difference. So the first term is very simple. We just look at the very first term in the sequence, the number that we started on. In this case, it is negative 5.4. And then our common difference. And our common difference, again, is just the difference between the new minus the previous, new minus the previous. So if we do, for example, negative 6.6 minus a negative becomes a plus. So negative 6.6 minus negative 5.5 or plus 5.5 is negative 1.2. And you are welcome to test that on a calculator just to be sure. Okay. So as long as I have those now, I can insert them into the explicit formula. So the explicit formula is a sub n, meaning I can find any term, as long as I start at negative 5.4. That's my first term. And then plus that common difference. Well, plus a negative is the same thing as minus here. That negative 1.2 and minus 1. So all I did was take that formula and insert that first difference, that first term and the common difference. Now let's go ahead and simplify. So to simplify, we distribute and we combine like terms. That's always the game when we're simplifying, is basically do any math that you can. So if we distribute that negative 1.2, negative 1.2 times n is negative 1.2n, and then we'll distribute it to the back here. Negative 1.2 times a negative 1, negative times a negative is a positive, and it's going to stay 1.2. And then we combine like terms. So we distributed the d value of negative 1.2, we distributed that, and now we have a couple of like terms right here that can combine. So when we combine that negative 5.4 with that positive 1.2, we get negative 4.2. So this is the explicit formula. And then we have, oh, I think I wrote that wrong. Hang on real quick. And so after combining, we end up with that negative 1.2n and that negative 4.2 constant. That's our explicit, and it does have that y equals mx plus b style. So definitely still kind of, channeling that linear relationship. Now that we have our explicit formula, let's go ahead and box that. We can find the 10th term. So now all I have to do is plug in a 10 for n. So for this one here, we would say a sub 10 is just going to be equal to negative 1.2 times 10 minus 4.2. And then we just evaluate that. And when we do that, we realize the 10th term is negative 16.2. So that's just throwing that in the calculator or being careful with doing that math. Let's try another one. Okay, let's see, how about let's try number 20. So on number 20, we want to do the same two things. We want to find the arithmetic sequence or the equation for the arithmetic sequence and then use that for the 10th term. So all I need to do, or I need to find, is the first term and the common difference for this sequence. The first term is 34. I can see that here. That's our beginning number. And our common difference is 3. They're adding 3 every time. 37 minus 34 is 3. 40 minus 37 is 3. 43 minus 40 is 3, and so forth. So that is our common difference right there. Okay, so we'll put that into the explicit formula, a sub n. I have it right here for reference. The first number plus that d value times n minus 1. We'll distribute the 3. So that's 3n, and 3 and negative 1 is a negative 3. And then I'll combine my like terms. So the equation would be 3n, and then 34 minus 3 is 31. Okay, and that is the explicit formula for that sequence. And once I have that, then I can find the 10th term by simply inserting a 10 for n and evaluating that. The 10th term would just be 61. 30 times 10 is 30, and 30 plus 31 is 61. There's the 10th term. Okay, so that's how we use the explicit formula to find any term. And we use 10, but we could have found the 435th term by just plugging in 435. So that's the beauty of it. You don't have to extend it out to find those values. All right, let's finish off with this word problem. It says in an auditorium, the first row of seats has 30 seats. Each row behind the first row has 4 more seats than the row in front of it. So how many seats are in the 25th row? So let's talk about that. If I started kind of making a list of values here, the very first row where we begin has 30 seats. And then what we know is that each row behind the first one has 4 more seats than the previous. So if this is 30, then the next row is going to have 34. The next one's going to have 38, 42, and so on, right? So that's essentially our sequence or our pattern. We start with a row of 30, and every row after that has 4 more, okay? So if we sort of translate that now to arithmetic sequences, what that tells us is that our first term is 30. That's our first row. And the common difference is what this is increasing by, which in this case is just 4. They want to know how many would be on the 25th row. So they're trying to find a sub 25. And so we definitely don't want to extend this 25 values. We can use our explicit formula to do that. So this is our formula one more time. First term plus the common difference times n minus 1. Let's insert the two values we know. This part stays. So the first term in the sequence is 30. Common difference is 4. So it looks like this. And then we distribute the 4 and simplify. So here it'll be 4 times n and 4 times negative 4. Combine our like terms, so it ends up being 4n plus 26. That's our explicit formula for this situation here, the auditorium chairs and rows. So once I have my explicit formula, then I can use it to really answer their question, which is how many seats would be on the 25th row. So all I have to do is insert a 25. The 25th row in the auditorium would have 100 plus, sorry, I didn't mean to do that. My head got ahead of me. It was just 26. This comes out to 100. So together it ends up being 126. Okay, so there would be, the 25th row has 126 seats. All right, there you go. Some days are easier than others to let's see. So the 25th row has 126 seats. There you go. And that's arithmetic sequence.